Welcome to today's problem walkthrough. In this session, we'll tackle LeetCode problem number 2149, rearrange array elements by sign. This is an interesting and practical problem that challenges us to rearrange an array so that positive and negative integers alternate, starting with a positive number. I'll guide you through the problem, the approach, and its implementation. Let's dive in. In this problem, we are given a zero-indexed integer array called nums. The array has an even length, and it contains an equal number of positive and negative integers. Our objective is to rearrange the elements of this array such that every positive integer is immediately followed by a negative integer. Furthermore, the relative order of the positive integers and the negative integers must be preserved, meaning that the sequence in which they appear in the input array should remain unchanged. Once rearranged, the function should return the resulting array. For the input format, nums will always be an array of integers where its length is even and can range from 2 to 100,000. The output format is simply the rearranged array that satisfies these requirements. Let's look at an example to better understand the problem. Suppose the input array is nums equals 3, 1, minus 2, minus 5, 2, minus 4. Here, the positive integers in the array are 3, 1, 2, and the negative integers are -2, -5, -4. To rearrange the array, we alternate between positive and negative integers while preserving their original relative order. This gives us the output 3, -2, 1, -5, 2, -4. Another example is nums equals -1, 1. In this case, the positive integer is 1 and the negative integer is -1. Rearranging them alternately results in the output 1, -1. Looking more closely at the explanation for nums equals -1, 1, we observe that since there is only one positive and one negative integer, the output is simply 1, -1, alternating between the two. Now, let's consider the constraints of the problem. First, the length of the array is always even and ranges between 2 and 100,000. Second, the absolute value of each integer in the array lies between 1 and 100,000. Lastly, the array always contains an equal number of positive and negative integers, ensuring that a perfect alternation is always possible. These constraints guarantee that the problem is well defined and that a valid solution will exist for all inputs. To handle edge cases, consider a few important scenarios. If the array length is at its smallest, such as nums equals 1, -1, the output remains 1, -1, since there's only one pair of integers to alternate. When the array contains large values close to the upper limit, or if it is already sorted or in reverse order, the solution must still preserve the relative order of positive and negative integers. For instance, nums equals -5, -4, 3, 2 would result in 3, -5, 2, -4. If the array contains repeated values, such as nums equals 2, 2, -3, -3, the output would be 2, -3, 2, -3, ensuring that the order of repetitions is preserved. These considerations help ensure the solution is robust and handles all possible cases. To solve the problem of rearranging an array so that positive and negative integers alternate, starting with a positive number, we can explore several approaches. One such method is the brute force approach, which involves separating the positive and negative numbers into two different arrays. From there, the result array is built by alternately picking elements from these two lists. This approach is very straightforward. First, we traverse the input array to create separate lists for positive and negative numbers. Then, using a loop, we alternate between these lists to construct the final array. While the time complexity is efficient at O(n), since we only traverse the array twice, the space complexity is a drawback, as we require additional storage equivalent to the size of the input. The simplicity of this approach makes it easy to understand and debug, but its reliance on extra space may not be ideal for all scenarios. Another way to solve this problem is through in-place rearrangement using two pointers. This approach eliminates the need for extra storage by directly rearranging elements within the input array. To achieve this, we use two pointers, one to track the next positive number and the other for the next negative number. Starting from the beginning of the array, we traverse it and rearrange elements such that positive and negative numbers alternate. The swapping ensures that the order remains consistent throughout the traversal. This method is highly efficient in terms of both time and space, with a time complexity of O(n) and a space complexity of O(1). However, managing the indices and swaps introduces additional complexity, which might make the implementation slightly more challenging. Despite this, the approach is optimal for scenarios where minimizing space usage is a priority. An even simpler method to solve the problem is the single-pass approach with direct placement. This technique uses an output array and counters to place elements directly at their correct positions. The steps are straightforward. We initialize two counters, one for the next positive index and the other for the next negative index. As we traverse the input array, we check the sign of each number. Positive numbers are placed at the next available positive index, while negative numbers go to the next negative index, with the respective counters increment each time. This process continues until the array is fully rearranged. The time complexity remains O(n), as each element is processed only once, but the space complexity increases to O(n) due to the use of an output array. The simplicity of this approach makes it easier to implement and debug compared to in-place rearrangement, which is why it is often preferred for coding interviews. For this problem, the single-pass approach with direct placement is the most practical and balanced solution. Although the in-place rearrangement method is more space-efficient, its complexity in managing indices and swaps makes it more error-prone, especially under time constraints. The brute force approach, while simple, is less efficient due to its reliance on additional space for intermediate lists. What makes the single-pass approach stand out is the guarantee of an equal number of positive and negative integers, which eliminates edge cases and simplifies the implementation. By directly placing elements at their correct positions during traversal, we reduce the need for multiple passes or complex logic. This method offers an excellent balance between clarity and efficiency, with a time complexity of O(n) and a straightforward implementation that minimizes coding errors. While it does require extra space for the output array, this trade-off is acceptable given the clarity and reduced risk of mistakes, making it ideal for both interviews and real-world applications. The problem we are solving involves rearranging an array of even length so that positive and negative integers alternate, starting with a positive integer. The array is guaranteed to have an equal number of positive and negative integers, which simplifies our approach. For example, given the input 3, 1, -2, -5, 2, -4, the output should be 3, -2, 1, -5, 2, -4. This ensures that positives and negatives alternate while maintaining their order of appearance. The constraints ensure that the array length is always even, and we never have a mismatch between the number of positives and negatives, which allows us to focus purely on the rearrangement logic without worrying about edge cases like uneven counts. To solve this problem efficiently, we use a two-pointer approach that takes advantage of the even distribution of positive and negative integers. First, we initialize two pointers. POS_IDX starts at 0 for the positions where positive integers will be placed, and neg_IDX starts at 1 for the positions where negative integers will go. This setup aligns with the requirement that positives occupy even indices and negatives occupy odd indices. Next, we create an empty array called result with the same length as the input array. This result array will store the rearranged elements, ensuring that we can manage placements without overwriting any values from the input array during the process. The next step is to iterate through the input array using a for loop. For each element, we check whether it is positive or negative. If the element is positive, we place it at the current POS_IDX in the result array and then increment POS_IDX by 2 to move to the next even index. If the element is negative, we place it at the current neg_IDX and increment neg_IDX by 2 to move to the next odd index. This alternating placement ensures that the positives and negatives are distributed correctly. Once all elements in the input array are processed, the result array will contain the rearranged elements in the required alternating pattern. Using two pointers allows us to independently manage the placement of positives and negatives without worrying about running out of slots. While it's possible to solve this in place with swaps, the additional array simplifies the implementation and avoids the complexities of managing indices in the original array. The algorithm relies on three key data structures. First, the input array is used to iterate through the elements and check whether they are positive or negative. Second, the result array stores the rearranged elements and simplifies the placement logic by avoiding overwrites. Finally, the two pointers, POS_IDX and neg_IDX, track the next available positions for positive and negative integers, respectively. These pointers ensure that each group is placed in the correct alternating indices. In terms of complexity, the time complexity is O(n), because we only traverse the input array once. The space complexity is O(n), due to the additional result array, which is the same size as the input. This trade-off in space for simplicity allows us to avoid more complex index management that would be required in an in-place solution. Let's walk through an example to see how the algorithm works step by step. For the input 3, 1, -2, -5, 2, -4, we start with POS_IDX equals 0, neg_IDX equals 1, and an empty result array initialized as 0, 0, 0, 0, 0, 0. As we traverse the array, the first element is 3, which is positive, so we place it at POS_IDX equals 0 and update POS_IDX to 2. Next, 1 is also positive, so we place it at POS_IDX equals 2 and update POS_IDX to 4. The third element, -2, is negative, so we place it at neg_IDX equals 1 and update neg_IDX to 3. Similarly, -5 is negative, so we place it at neg_IDX equals 3 and update neg_IDX to 5. The fifth element, 2, is positive, so we place it at POS_IDX equals 4 and update POS_IDX to 6. Finally, -4 is negative, so we place it at neg_IDX equals 5 and update neg_IDX to 7. The result array is now 3, -2, 1, -5, 2, -4, which is the correct output. Now, let's consider some edge cases and potential optimizations. For the smallest possible array, such as 1, -1, the output is simply 1, -1, as no rearrangement is needed. If all positive numbers appear first, such as 2, 4, -1, -3, the algorithm ensures that the output alternates correctly as 2, -1, 4, -3. Similarly, if all negatives appear first, like -1, -3, 2, 4, the output will still alternate as 2, -1, 4, -3. An optimization to reduce space complexity would be to rearrange the input array in place using swaps, but this increases the complexity of managing indices. By using an additional array, we keep the implementation straightforward and reduce the likelihood of errors, making the solution easier to implement and debug. This Python implementation solves LeetCode problem 2149, rearrange array elements by sign. The goal is to rearrange an input array such that positive and negative integers alternate, starting with a positive integer. The input array is guaranteed to have an even length, and it contains an equal number of positive and negative integers. The code begins by separating the positive and negative integers into two separate lists, positives and negatives. This is achieved using a simple for loop that iterates through the input array. If a number is greater than 0, it is added to the positives list, otherwise, it is added to the negatives list. Once the positive and negative numbers are segregated, the next step is to interleave them into the final result. This is done using another loop that iterates through the indices of the positives list. For each index, the corresponding positive number is appended to the result list first, followed by the corresponding negative number. This ensures the alternating pattern of positive and negative integers. Finally, the function returns the result list, which contains the rearranged elements following the desired pattern. The implementation is efficient, with a time complexity of O(n), where n is the length of the input array. This is because both the separation and interleaving processes involve single linear passes through the data. The space complexity is also O(n), as additional lists are used to store the separated positive and negative numbers. This solution is concise, easy to understand, and adheres to the problem's constraints, ensuring correctness and optimal performance. Here, we begin by importing the necessary Java utilities and defining our solution class. Within this class, we have the Rearrange array method, which takes an array of integers as input. To start solving the problem, we create two separate lists, one for positive numbers and another for negative numbers. This helps us organize the input array into two distinct groups. Next, we iterate over the nums array using a for each loop. For each number, we check if it is positive or negative. If positive, we add it to the positives list, otherwise, it goes into the negatives list. These lists will store the numbers while maintaining their respective order from the input array. Once the lists are populated, we proceed to interleave the positive and negative numbers into the result array. To do this, we initialize an empty array named result with the same length as the input array and set up an index variable to track our position in the resulting array. Using a for loop that iterates through the positives list, we alternate between adding one positive number and one negative number to the result array, incrementing the index after each addition. This ensures that the numbers are interleaved correctly, as required by the problem statement. Finally, the result array is returned once all elements are processed. And that's all there is to the implementation. The method concludes by returning the interleaved array, which meets the requirements of the problem. By keeping the positive and negative numbers in separate lists and carefully alternating them in the output, we ensure that the solution is both simple and efficient. This approach leverages the order-preserving properties of array lists and avoids the need for complex data structures, making it a clean and effective solution. In this problem, we are given an array of integers where the count of positive and negative numbers is equal. Our task is to rearrange the array so that every positive number is directly followed by a negative number. Importantly, we must preserve the relative order of both the positive and negative numbers from the input array. To achieve this, we will first separate the positive and negative numbers into two separate lists, and then interleave them to form the desired arrangement. For instance, consider the input array 3, 1, -2, -5, 2, -4. We start by initializing three empty lists, positives to hold the positive numbers, negatives to hold the negative numbers, and result to store the rearranged array. Let's break this process down step by step. The first step is to separate the positive and negative numbers from the input array. We iterate through each number in nums. When the number is greater than 0, we add it to the positives list, and when it's less than 0, we add it to the negatives list. For the given input, 3, 1, -2, -5, 2, -4, the first number is 3, which is positive, so it's added to positives, making it 3. The next number, 1, is also positive and is added, updating positives to 3, 1. The third number, -2, is negative, so it's added to negatives, resulting in -2. This process continues for each element in the array, leading to a final separation where positives equals 3, 1, 2, and negatives equals -2, -5, -4. Now that we have our two lists, the next step is to combine them in an interleaved manner. We take turns adding one positive and one negative number to the result list. Starting with the first positive number, 3, we add it to result, making it 3. Then, we add the first negative number, -2, updating result to 3, -2. This alternating process continues until all numbers are added, producing the final list, 3, -2, 1, -5, 2, -4. At the end of this process, the rearranged array is 3, -2, 1, -5, 2, -4. This output satisfies the requirement that each positive number is followed by a negative number, and the relative order of the positive and negative numbers from the input is preserved. Let's now look at another example to reinforce this approach. Consider the input array 5, -1, -2, 4, -3, 6. We begin by initializing three empty lists, positives, negatives, and result. The goal remains the same, to separate the numbers into positive and negative lists, and then interleave them. First, we separate the numbers by iterating through the input array. For the first number, 5, which is positive, we add it to positives, making it 5. The next number, -1, is negative and is added to negatives, resulting in -1. The third number, -2, is also negative, so it's added to negatives, updating it to -1, -2. The fourth number, 4, is positive and is added to positives, making it 5, 4. Continuing this process for the remaining numbers, negatives becomes -1, -2, -3, and positives becomes 5, 4, 6. Next, we interleave these lists. Starting with positives, 0 equals 5, we add it to result, making it 5. Then, we add negatives, 0 equals -1, updating result to 5, -1. Following the same alternating pattern, we add 4, -2, 6, and -3 in sequence, resulting in the final output, 5, -1, 4, -2, 6, -3. This output, 5, -1, 4, -2, 6, -3, once again ensures that each positive number is followed by a negative number while maintaining their relative order. Let's analyze one more example to solidify this concept. Consider the input array 1, -1, 2, -2, 3, -3. As before, we start with 3 empty lists, positives, negatives, and result. The separation step begins by iterating through the array. The first number, 1, is positive, so it's added to positives, making it 1. The next number, -1, is negative and is added to negatives, resulting in -1. This process continues for all elements, leading to positives equals 1, 2, 3, and negatives equals -1, -2, -3. Now, we interleave these lists to create the rearranged array. Starting with the first positive number, 1, we add it to result, making it 1. Then, we add the first negative number, -1, updating result to 1, -1. Continuing this alternating pattern, we add 2, -2, 3, and -3 in sequence, resulting in the final output, 1, -1, 2, -2, 3, -3. This output satisfies the problem's requirements, as every positive number is followed by a negative number, and their relative order is preserved. By following these steps, separating the numbers into 2 lists and then interleaving them, you can solve the problem efficiently for any valid input. In this solution, the time complexity is determined by 2 main operations, separating the input array into positive and negative numbers, and then interleaving those 2 lists to create the final result. First, when we separate the elements of the input array nums, we iterate through each element using a for loop. For each number, we check if it is positive or negative and append it to the respective list. Since appending to a list is an O(1) operation and the loop runs n times, where n is the size of the input array, this entire step takes O(n) time. Next, we interleave the positive and negative lists to form the final result. The interleaving process iterates through half of the total elements, approximately n/2, as the positive and negative lists collectively contain all elements from the input. During each iteration, we perform 2 append operations to the result list, both of which are O(1). Consequently, this step also takes O(n) time. Combining both steps, the total time complexity of the solution is O(n) plus O(n), which simplifies to O(n). Now, let us analyze the space complexity of the solution. The input array nums is provided as part of the problem, so it does not contribute to additional space usage. However, we use 2 auxiliary lists, positives and negatives, to store the positive and negative elements from nums. Since every element in nums is either positive or negative, the combined size of these 2 lists is equal to n, the size of the input array. Additionally, we create a result list to store the interleaved positive and negative numbers, which also has a size of n. Apart from these lists, there are a few temporary variables, such as number and I, which consume constant space, or O(1). Therefore, the total auxiliary space usage comes from the positives, negatives, and result lists, which together require O(n) space. As a result, the overall space complexity of the solution is O(n). To better understand the efficiency of this solution, let us compare it to a potential brute force approach. A naive solution might involve iterating through the input array nums multiple times to alternately pick the next positive and negative numbers. This would require additional loops or more complex conditional checks, resulting in a time complexity of O(n) squared, in the worst case. On the other hand, the space complexity of the brute force method might still remain O(n) if intermediate lists are used to store the results. In contrast, the current solution is far more optimal. By processing the input in a single pass to separate the numbers and another pass to interleave them, we achieve a linear time complexity of O(n). The space complexity is also O(n) due to the auxiliary lists used for storing the positive, negative, and final interleaved results. Overall, this approach provides an efficient balance between time and space, making it a highly optimal solution for the problem. Brute force alternatives, while functional, would be significantly less efficient, particularly in terms of time complexity. When working on this problem, there are several common mistakes to watch out for. First, many people overlook the requirement to maintain the original order of positive and negative numbers. Simply rearranging them randomly is not enough. If the relative order of the elements in each group changes, the solution will be considered incorrect. Another frequent misunderstanding arises with arrays of odd length. Some assume the input array might not always have an even number of elements, leading to unnecessary complexity in their implementation. However, the problem guarantees an even length, so this extra effort is redundant. Finally, incorrect indexing is a frequent issue. If you use just one pointer for both positives and negatives or fail to alternate properly, it can cause clusters of positive or negative numbers, violating the problem's alternation requirement. These are critical aspects to keep in mind as you work through the problem. Another mistake to avoid is relying on inefficient solutions, such as nested loops. For example, repeatedly searching for the next positive or negative element results in an n² time complexity, which becomes impractical for larger arrays and can even lead to time limit exceeded errors. Equally important is understanding the problem's constraints. Some might unnecessarily check if the input array contains an equal number of positive and negative integers. This check is redundant because the problem guarantees this condition. Adding extra validations wastes time and clutters your solution, so it's better to trust the constraints and focus on the core logic. To succeed in interviews, focus on recognizing the underlying pattern. A key insight is to separate the positives and negatives into two lists or queues, and then merge them alternately. This approach ensures the correct order while maintaining simplicity. An optimal solution will use O(n) space to store these separate lists and O(n) time to merge them. For those aiming to optimize further, an in-place solution can reduce space complexity, but it's more challenging to implement correctly. Be mindful of edge cases as well. While the problem guarantees even length arrays and equal numbers of positive and negative integers, interviewers might ask about additional constraints or invalid inputs. It's also common to encounter follow-up questions that explore variations, such as rearranging based on odd and even numbers or processing data streams. For further practice, related problems like sort array by parity to or wiggle sort can help strengthen your understanding of similar concepts. There are also alternative approaches to solving this problem, each with its own trade-offs. The two-pointer technique is one option. Here, you use two pointers, one for positive numbers and one for negative numbers, to traverse the array and swap elements in place. While this method reduces space complexity to O(1), it can be harder to implement and debug. Another approach is to store positives and negatives in separate arrays and then merge them alternately into a new array. This method is simple and intuitive but requires O(n) extra space. A third option is in-place rearrangement, where you directly modify the array by keeping track of the next available slots for positive and negative numbers. This approach saves space but is more complex to implement, especially while ensuring the order of elements is preserved. Choosing the right method depends on the specific constraints and requirements of the problem or interview scenario. Great work! To summarize, we solved the problem by alternating positive and negative integers, leveraging efficient array manipulation techniques. Remember to apply these strategies to similar problems you encounter. Thank you for watching, and be sure to like and subscribe for more content. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!